So did you get one? I hope so. When we do this integral, we're going to have the upper limit be b and take the limit as b approaches infinity. The antiderivative of x to the negative 2 is negative x to the negative 1. When I do the limit, I'm only going to do the limit on the part of the antiderivative that includes the b, the part of the antiderivative where I'm plugging in the 1. I'm going to leave where it is. Of course, this is negative, so when I do minus for fundamental theorem of calculus, I get plus 1. This limit is equal to 0. Limit is b approaches infinity of negative 1 over b, because the numerator is bounded, but the denominator increases without bound. So I end up with 0 for that limit, and plus 1 over 1 is 1. Okay, so that's what this integral is equal to 1, the integral from 1 to infinity. All right, so what does this integral tell us about the sum that we want to do? Well, I've drawn a picture here of f of x equals 1 over x squared. That's what we did the integral of. All right, and then what I've done here is I've started to build in a right-hand sum with delta x equals 1. Now, f of x is a decreasing function critically, and I'm estimating with a right-hand sum. Therefore, the right-hand sum is going to be an underestimate. The right-hand sum is less than the integral. But what is this sum? Well, this sum is, our delta x's are all 1. So this rectangle is 1 times, 1 over x squared. So it's 1 over 2 squared, 1/4. So this area is 1/4. This area is 1 times 1 over 3 squared. So it's 1/9. This one's 1/16, and so on. So in fact, this is actually a chunk of our series. Our series 1/4 plus 1/9 plus 1/16 plus 1/25 plus etc. All right, so I could, by the way, build another block over here and say I'm doing a right-hand sum over here, and there's a 1 over there. I don't think that much affects our calculation here. What's important is the integral that we did was from 1 to infinity. So this area, all right, the green area here, including the rectangles, that area is equal to 1. That's, and this chunk of the integral is less than that because it's an underestimate. We have a right-hand sum on a decreasing function is an underestimate. So the right-hand sum is an underestimate of the integral. The right-hand sum is less than the value of the integral. That means that this part of our sum, taken all the way to infinity, is less than 1. But of course I had 1 to start with, so I have to add, I'm doing 1 plus something that is less than 1. So the conclusion that I arrive at here is not only does the sum from n equals 1 to infinity of 1 over n squared converge, but also the sum from n equals 1 to infinity of 1 over n squared is less than 2. All right? So that sum is less than 2, but so my integral being 1 told me that the sum converges, but doesn't tell me anything about the value that I'm converging to, because I can see that, I'm getting to 1.6349, 1.6439. This sum is not going to get up to 2. And in fact, I can make a more compelling argument by seeing that the actual sum is clearly less than the integral. So the fact that the integral converges tells us that the sum converges, but does not tell us the value of the sum. All right, so that in fact is our theorem. And so let me also mention again that the function that I'm using has to be decreasing, because otherwise the sum's not an underestimate. All right, so the worst thing is if it starts increasing and going like that. All right, then I can't use the integral to estimate the sum anymore. All right, the function has to be decreasing. The function also has to be positive. All right, the function has to be positive, decreasing, and continuous. So it's sort of a lot of conditions on this one. So hopefully we'll get some other kinds of criteria later. All right, so here's what we have. If f of n equals a sub n for all n that are natural numbers, where f is a decreasing, positive, continuous function, and in order to be continuous function, it has to have domain real numbers, whose domain is real numbers. Then the sum from n equals 1 to infinity of a sub n converges if and only if the integral from 1 to infinity of f of x dx converges. So the integral and the sum converge and diverge together. So this is something called the integral test. So I guess more fully we would say the integral test for the convergence of series. But we usually just call it the integral test. Now, where you're going to find this lovely integral test, if I can get to the right page here, is not in your nice orange book. Now, here we go. Okay. Meet your new friends, Stewart and Kokoska. So you may have noticed that in the website posting for textbook, there are a number of chapters, starting with chapter 9, that are listed as Stewart Kokoska. That is this book. This book has a much better development of series than your orange book does. So for the rest of this chapter, we're not going to use the orange book. We're going to use Stewart Kokoska. All right, and so where the integral test appears is in section 9.3, because we already did 9.1 and 9.2, and then we're just going to go section by section. The integral test. It is on page 677 of section 9.3. All right, so they just call it the integral test. Most people do. F is continuous, positive, decreasing. A sub n equals f of n. I should say for all natural numbers n. Then the series is convergent if and only if the improper integral from 1 to infinity f of x dx is convergent. All right, and they break it down into two parts. If the integral converges, then the sum converges. If the integral diverges, then the sum diverges, which is nice. But all you need to say is this. All right, now a quick word about our friend Stewart Kokoska and reading the book. This is the most readable textbook I've ever seen. From now on, I strongly encourage you to actually read the section. So the section we're on is 9.3. You should just read through it. It's very well written. It's easy to understand, and it's a really nice resource that you have. All right, so we're doing section 9.3. It's posted on the website. This is the integral test. In the next couple of videos, we're going to see how to use it to determine if things converge or not, and by looking at some of the homework that is going to come from Stewart Kokoska.